using our understanding of instantaneous velocity as the slope on our position versus time graph, let's see if we can find the velocity for this situation here. So we're going to draw a velocity versus time graph based on this position versus time graph. Let's begin by noting that it seems like there are three main sections here that we're looking at. And so we can break this into a few different sections. Let's start by saying, all right, right here, seems like one section, this is another section, and we'll label these sections as this will be 1, 2, and 3. And we can consider some initial time 0. This at the transition between 1 and 2 we'll call time 1 right there. This will be time 2. And you could consider some other time 3 over here. So if I want to find the velocity from this graph, I want to find the slope along here. And luckily, I don't have to do an instantaneous velocity thing. It's not like curving around. The slope here is a constant throughout here. So if I just find the slope, I can use any 2 points along this region to find this slope. So I'm going to go ahead and use this point up here. So time 1 and time 0 with the positions x1 and x0. So we'll say that my velocity, my average velocity for that region 1 is going to be equal to my final position x1 minus my initial position x0 over the elapsed time, time 1 minus time 0. We'll plug those in and we get 0.5 minus 0 divided by 0.5 minus 0. The units on the top are meters, the units on the bottom are seconds. And so we end up with 1 meters per second. Lovely. We can now draw this on a plot here. I'll go ahead and put this down here. So this will be, it looks like the important places are, we're going to have a time of 0.5. We'll have a time of 1, it looks like. And then the next important time will be 2. So this will be 1, and this over here will be 2. Okay, so that's my time, and then what we're plotting here will be velocity. So time will be units of seconds, and velocity will be units of meters per second. So now when I plot this here, it looks like we have 1, and that's true up until 0.5 seconds. So 1 up until 0.5 seconds. Let's consider the second region now. My average velocity for the second region is going to be my final position minus my initial position. And here it's going to be my position evaluated at time 2 minus my position evaluated at time 1 divided by the elapsed time, time 2 minus time 1. So here I'm at 0.5 for both of these. So 0.5 meters minus 0.5 meters divided by, turns out it doesn't matter what's going on with the times here. Since we haven't moved, our velocity is going to be 0. But let's go ahead and plug in the times just to make sure we know what we're doing. 1 second is my final time, 0.5 seconds is my initial time. And so we end up with 0. So I can say that from this region, from 0.5 to 1, we're at 0. And we'll worry about what's happening in between in just a second. Let's consider my third region. Average velocity for region 3 will be x3 minus x2 over t3 minus t2. Finally, I end up at position 0. Initially, I was at position 0.5. And that's just reading off the chart over here. Initially, I was at 0.5. Finally, I'm at 0. And then time-wise, it's 2 seconds minus 1 second. So when we divide those, we get a minus on top and 1/2. So minus 0.5 meters per second. So we can put that on the plot here as well. Something about right there, it looks like, where that is minus 0.5. Lovely. What about in between here? Well, if you approach it from one side versus the other side, you end up with a different slope. So coming from the left, you have a slope of 1. Coming from the right, you have a slope of 0. So that means that the value, if we're trying to evaluate it, like what is my actual velocity at this point, doesn't have a well-defined mathematical term. But in terms of physical significance, this is where the physics part of it means this is not just a math problem. We're looking at physically what's happening. In order to go from moving with some positive velocity to some zero velocity, you kind of have to pass through in between stages there as you're doing that. So this very sharp curve here doesn't really correspond to what you would expect to see in a real physical situation. So I'm pretty comfortable connecting these here, knowing that, all right, it's not that it's simultaneously all these different values here. It's that this is a mathematical model that doesn't actually capture the full details of what's physically going on here, if this is a real thing moving around. And so when we draw this, this is just indicating that, well, it's very fast. We don't actually have information about how this changes, but you can imagine if the actual behavior rounded over a little bit, then we could use that and parameterize that to figure out how this velocity changes between there. So that's why I'm connecting these, even though mathematically you might be a little bit leery about connecting them like that. We don't have information about what's going on over here, so I'm not going to pull it back to 0 at the end, but that's that. That's taking a position versus time plot and looking at the slopes of that plot in order to make a velocity versus time plot. So position versus time, the slope gives you velocity, so we use that to find the velocity.